In this lesson, we're going to talk about electric fields. Here are your objectives. So before we talk about what fields are, let's talk about why we need them. The electric force, like the gravitational force, is an action at a distance force. Meaning, in contrast to a force like a normal force or a force of tension where we have two objects in contact, for the electric force, like the gravitational force, we've got objects that are seemingly separated by a distance and yet exerting a force on each other. Here, a proton and an electron are at a distance but pulling on each other. And so we need a way of thinking about that, and fields are the way that physicists do that. A field is a region in space where a force is felt. So let's just stop for a moment and think about a grassy field and look at the wind on that field. You could ask yourself, okay, in which direction and how hard is the wind blowing at all different points on this field? And let's say it's blowing very hard over here in the same direction but less hard here and less hard there, and then it's in a slightly different direction at other points on the field. So what these arrows are representing is how hard and in what direction the wind is blowing. This is a vector field. It's showing both direction and magnitude of the wind at all of these different points. And that's very similar to the way that we're going to use fields for the electric force and the gravitational force. What we will say is that the first charge, let's say the proton, creates a region in space around it composed of possible forces that we represent with arrows like this, and then when the electron sits in that field, it feels a force. So the electric field is this vector field. It's a region in space around a charge where a force can be felt. To illustrate, this simulation is from PhET, the URL is here, and we've got an empty region of space. I'm going to take a positive 1 nanocoulomb charge and I'm going to place it here, and notice that I now have arrows around it radiating outwards from the positive charge. So by Coulomb's law, we know that the farther you get from a charge, the weaker the force gets, and so that's being illustrated here by the brightness of the arrows. Brighter arrows meaning stronger forces, and dimmer arrows weaker forces. Also notice that the forces are pointing outwards from a positive charge, so they are representing the direction of force a second positive charge would feel. I can actually map that out more specifically by taking this sensor, which is itself a tiny positive charge, and moving it around. And you can see the red line is the force that it would feel. As I move it closer to the positive charge, the force it feels gets larger, indicated by a longer arrow, and as I move it farther away, that force gets smaller and smaller. And so we could actually map out this whole region around it by moving this sensor, which we call a test charge, around and then drawing little arrows onto the region in space. And that's what is actually shown here by the brighter and dimmer white arrows. So the field is this region in space where a force could be felt, and it's created by this positive charge that we've placed here. If I were to place a negative charge here, then I will still get a field, but notice that the arrows are now pointing inwards towards the negative charge. Again, the test charge that we're using, this sensor, is itself a positive charge. And so if we map out the region in space, that force is always going to point inwards towards the negative charge, and so the field does as well. Now, the magnitude of the field is a kind of per capita force. Let me explain what I mean by that. We define the electric field as the force per unit charge. So here, this is the electric field. It's a vector, just like the force is a vector, and they have the same direction. So the electric field is equal to the force divided by Q, which is the magnitude of a test charge. It's that little yellow sensor, which was itself a positive charge that we were moving around. So the electric field is the force per unit charge. It's like a per capita force, in the same way that if you were comparing the United States and Canada, let's say their economy, you wouldn't want to compare their economies directly, you'd compare them per person, per capita, so dividing by the number of people. In the same way here, you're dividing by the unit charge. A larger charge is going to feel a larger force, but by dividing out that charge, you get a way of mapping out the field itself. Now, because we are dividing force, which is in newtons, by charge, which is in coulombs, the unit of the electric field is newtons per coulomb. And again, the test charge that we use is positive, and so the direction of the electric field is the direction that a positive charge would feel a force. It's the direction of the force on a positive charge. And that test charge itself has just a tiny amount of charge. We want that because if it were bigger, it might cause the first charges to actually move. So we don't want the first charges, that red or blue charge that I put there in the simulation, to move. So the charge on the yellow test charge has to be tiny in amount. Back to the simulation, what if I have multiple charges that are creating the field? So here I've got 3 charges. If I were to put my sensor here in the middle, the force that it's going to feel is going to be a combination of forces from all 3 charges, and therefore the field is as well. The field is a vector field. It's the sum of the force per capita, if you want to think of it that way, from all of the other charges around. So again, the electric field is a vector field, and the force per coulomb on the test charge at any point is the vector sum of the forces from the different charged objects. So we saw that if I have a positive charge and a positive charge and a negative charge over here, then I'm looking at the force here per unit charge as a result of all of these, which might be, for example, like that. Now, if we want to draw what we're seeing in the simulation, we can't use brightness and dimness in order to represent the magnitude. So let's put a positive charge there at the center. If we move the yellow test charge around, again, what we saw was that if we were really close by, we saw a really big force. If we were further away, let's say over here, we would see a weaker force. And if we were further away, let's say over here, we saw a weaker force. And we can see that the pattern is going to be that they are going to radiate out in all directions. So if I just choose some spots to draw arrows from, let's say I choose that spot, that spot, that spot, and that spot, and I'll do this in all directions, then we know that the arrows are going to get shorter as I move out, and these are all meant to be about the same length and the same distance. And again, if I am out here, then they're going to be shorter. But you can see that I can choose a point that is being covered up by one of the vector arrows and try and draw a line there as well. So this gets very, very messy, but you get the idea. And in the next lesson, we'll talk about a way of dealing with this messiness. But the vector field created around a charge is indicating the magnitude and direction that a test charge, a small positive test charge, would feel a force. There's another pattern you should know, and that's the electric field of a parallel plate capacitor. Now, a parallel plate capacitor is where you have 2 conducting plates in parallel to each other, where one is charged positively, we'll make that the left one, and one is charged negatively, we'll make that the right one. And the field between those two turns out to be uniform. If I were to choose any points, I'll just choose these points to illustrate, then no matter where I am left to right on this, the force, or up or down, the force is always going to be the same. So all of the arrows that I should draw here will be all the same length. Imagine that these are all the same length. And again, this gets messy, and these arrows could be overlapping. I'm drawing them not for simplicity, but the idea is that the field is uniform, that no matter where I am in here, I'm going to experience the same force per unit charge, the same electric field. To illustrate that as best as I can in the simulation, I've tried to create that setup by just lining up point charges, and you can see that within an approximation, we've got these arrows that are pointing left to right in between the 2 plates. They do curve around the edges, but in between the 2 plates, they're pointing just left to right, more or less, and that the brightness is not diminishing. These are all the same brightness, which is what we are indicating by the length of the arrows, the magnitude, in the drawing. Lastly, let's derive a formula for the electric field of a point charge specifically. This won't work for a parallel plate capacitor, but it is for a point charge specifically. In general, and this is true for everything, the electric field is equal to the force per unit charge. But for a point charge specifically, we know that Coulomb's law tells us that the force, or the magnitude of the force, is equal to K1 times Q1 times Q2 divided by R squared. And let's say that this is the main charge, the red or the blue, and this is the test charge, our sensor in the simulation. And so we need to divide out the magnitude of the test charge. So we're going to divide out by Q2, and that gives us K times Q1 divided by R squared. Or sometimes you'll see this as big Q and this one is little q, so you might also see this written as K times big Q, that's the red or the blue central charge, divided by R squared. We've divided out the magnitude of the yellow test charge. So that's the electric field of a point charge as a formula, and that's your introduction to electric field.